The spherical snowball question. The spherical snowball is melting at a rate proportional to its surface area. That is, the rate at which the volume is decreasing at any instant is proportional to its surface area at that instant. Prove that the radius of the snowball is decreasing at a constant rate. Well, what are they asking for? The radius decreasing at a constant rate is dr dt. So that's what they want us to show, that this is equal to constant or equal to some letter. What other information have we got? Well, we know the volume of a sphere is 4/3 pi r cubed. So what we can do with this is, we know this is a differentiation rate of change question. dv dr is equal to 4 pi r squared, or 3 by 4/3 pi r squared. So if we create a chain rule with dr dt using this guy, dv dr dt is equal to dr dv, which will be this one upside down, times, so we want a dt on the bottom, so we're going to have to get rid of that dv. So these two things, these dv's will cancel. So we have dr dv is 1 over 4 pi r squared. So we need to get dv dt, and it tells us in the question volume is decreasing at any instant. So this is dv dt. It's proportional to its surface area. So surface area of a sphere is 4 pi r squared. So proportional to its surface area, this here would give us any, let's use the letter k times 4 pi r squared is the rate at which the volume is decreasing, a constant by the surface area, or something proportional is a constant. So if we fill that in down here, this k times 4 pi r squared, you can see what's going to happen here. The 4 pi r squares will cancel, leaving me with dr dt is equal to k. Second part of the question, if the snowball loses half its volume in 1 hour, how long does it take to melt completely? Right, well, if it loses half its volume, and the reason the radius is decreasing at a constant rate, so that means that after an hour it's still a sphere. So let's look at the two volumes then. We know the volume is 4/3 pi r cubed. So we're going to have different radiuses here, so they're the things that are going to change. So the radius initially is 4/3 pi r cubed, but half of that will be 2/3 pi r cubed. So that's going to be equal to the volume after 1 hour, which is still a sphere, 4/3 pi, and we need to change the radius, we'll call it r1. So half the initial amount is equal to what it is now. That's these two things equated. So if we can get, in terms of r1, the radius after an hour, that will tell us what the rate of change is. It'll have gone from r to r1, which will give us the rate of change. So we cancel our 3's and our pi's, and we're left with r cubed. We want r1, let's get r1. In terms of r1, it'll give us the rate of change. r1 cubed is equal to, that's this r1 here. We're going to bring the 4 underneath the 2, so that's 2 over 4 r cubed, the initial radius cubed. So the radius after an hour cubed is equal to a half the radius at the beginning cubed. So we can get the cube root of each side. This is a product, so the cube root of r cubed is r, and the cube root of 1 over 2. So r1 is equal to the cube root of 1 over 2 times r. So r1 is going to be equal to, the cube root of 1 is 1, and we can just write the cube root of 2. So let's not decimalize it yet, times r. So the rate of change then, if I come up here, the rate of change, it started at r, and after 1 hour, the radius was 1 over the cube root of 2 times r. So that's the rate of change. And if we imagine the total change over the rate of change, if we think, let's say it was 10 to begin with, let's say that was the total volume, and the rate of change was 2 per hour, reduced by 2 per hour, we'd see that that would be equal to, it would melt in 5 hours. So if we take the total change, so it's going to start at R, the radius, and what will happen when it's completely melted? It'll go to 0. So R is going to 0. And that will be over the rate of change, which is going from R, and we'd have to take away the rate. So after an hour, it was 1 over the cube root of 2 times R. So it goes from R to 0 on top, and the rate of change is R minus 1 over the cube root of 2 times R. So we can factorize out R here, actually. So if we divide each term by R, divide by R, we're going to have 1 on top, and on the bottom we're going to have 1 minus 1 over the cube root of 2. So that's how we can end up with just a number here. So if we type this into our calculators, it's going to give us, to 2 decimals, 4.85, and that would be an hour. So it's going to take 4.85 hours to melt. But I think the question asks how long more? How long does it take to melt completely? So this is how long it will take to melt completely, and we can just convert that into minutes. If we multiply by 60, we're going to get 290.84 approximately, or 291 minutes for the Snowball to melt completely.